Hello. So here is our video for the last 2 weeks. In week 3, we covered recursion, and in week 4, we covered sorting. And then next week, we're going to cover more sorting and complexity analysis. So for this video, we're going to focus mostly on recursion and do a little bit of sorting, since next week is going to cover more sorting and more complexity analysis. So let's talk about recursion. What is recursion? Well, recursion is essentially repetition without looping. So if we all know what a loop is, we can do a loop. So let's do a for loop. So do int I equals 0. So we have to initialize a counter to count how many times we're going to repeat the code. And then we're going to have some terminating condition. So when the loop's going to stop. So we can do, let's say, when I is less than 5. And then we're going to do something so we can increment towards the terminating condition. So we're going to start I at 0. And we're going to tell the computer that we wanted to loop a certain number of times until this condition is met. And now you have to tell it how we're going to meet the condition, and what we can do is we can increment I by 1. So that's I plus plus or I plus 1. Both of them do the same thing. So here's a basic loop. And in this loop, let's just make it print out I. So to print out something, we do std count, these less than signs, and then we do I, std window. So now we should get, if we compile this, we should get 0, 1, 2, 3, 4, 5. Oh, we get 4. Okay. So the reason why you don't get 5 is because when this ends up being 5 is less than or equal to 5, that's a false statement, so it terminates there. If we have 4, is 4 less than 5? Yes, we know that's true. But is 5 less than 5? No, so it terminates 1 before. This is also called an off by 1 error. So it's very common to happen in programming when everything's off by 1, and it's typically done with these types of things. So anyways, so that's a loop. And recursion allows us to basically loop without, or to repeat without having a loop. So if I wanted to write the same thing using recursion, here's how I would do it. So our recursive statement isn't gonna really return anything. So I'm gonna make a new function, make it void, because it's not gonna return anything. And I'm just gonna name it recursion. And it's basically gonna take in an integer, I, and we're gonna start it at equal to 0. So you see how this is the same as this? Okay. So we're going to start off there. And then, so for us to have the condition to when to tell the recursion to stop, so here this is the terminating condition. In recursion, we call it the base case. So like it's the condition when the recursion stops looping. So let's make the base case when I is equal to 5. So if I is equal to 5, yeah, let's do if I is equal to 5, then we're just going to return. So once a function returns, we're telling the compiler that the function is done running. So it is going to like note that the function is over, and then it's going to start to terminate. So yeah, so here we have our terminating condition. And now we have to do the same thing here. So we have to tell it to increment by 1 so we can inch towards the base case because we're starting at 0 and we have to increment by 1 so we can hit the base case and then terminate. So what we can do is we can call the function again, recursion, and what we do is we pass an I plus 1. So now this will run. It will go here. This will be false because 0 is not equal to 5. And we'll call the function again, but make this 1. Then it'll be 2, 3, 4, 5. So it will loop 5 times. And then it's going to return. And then the function is going to know that's over. And then it's going to go all the way back and then terminate. So we can print. So let's try to print. So count I. SCV. So these two loops should do the same thing. I think this one might actually print 5 though, because we're telling it, because we're going to call this before we call this. But if you wanted to print 4, we just write this here. Okay, so if my calculations are correct, and then we're just going to tell the function to terminate. So if my calculations are, actually I can just do this. If my calculations are correct, this thing should do the same as this. So let's try it out. Recursion. Cool. Okay, yeah, so here's our loop, 0, 1, 2, 3, 4, and here's our recursion, 0, 1, 2, 3, 4. So we've basically done looping in 2 different ways. One is using a for loop, and one is using recursion. So I'm gonna take a photo of this and try to walk you guys through how this is actually working, because there's some nuance with recursion that is pretty important, and it gives us some special benefits. Because normally you would say like, hey, look, I could write the same code in 3 lines that you did over here using like, I don't know, how many lines is that? Like 8 lines? You'd be like, "Oh, well, why would we ever use recursion when this is so much cleaner and easier to read, whereas this is complicated and convoluted and you have to make a function and everything?" Well, I will tell you why. So let's go to the iPad. Okay. Okay. So here's our code. So, like I said, this and this are doing the same thing. Recursion is just repetition without loops. So something to keep in mind here, like I said, is that this is our start, which is right here. This is our terminating case, which is right here, which in recursion we call the base case. And then we also have to increment towards the base case, and we do that here. So we basically call the function again, incrementing towards that base case. So again, we start off here. We make our conditional to when to terminate, and then we increment. So something to keep in mind with recursion is that recursion makes like different stack frames. So if you remember from my previous lecture, I talked about how memory works in the computer, and there's like something called a stack. And with stack, things are popped in. So functions are popped in. So the first function that always gets popped in is our main. So we have our main function. And basically the program, the computer knows that the program has done like executing once main leaves and the stack is empty, and then the operating system is like, hey, this program is now done. We can now use the memory that it once allocated for something else. So keep that in mind. So this loop actually takes place in memory here. So this loop lives in the main stack. But since this is a recursion function, because we have to call the function when we get to here, it does actually have its own stack frame. And by stack frame, I just mean like segments of like individual segments of the stack, like this. So think of it like bricks, like you're putting in bricks into the stack jar. And the reason why it uses jar analogy is that the stack memory has a special order that you have to adhere to. It's called last in, first out, or LIFO for short, LIFO, LIFO. So what this means is that, kind of like what the name suggests, the thing that gets put in last, so for example, let's say it's the stack frame, it will be the first one to leave. We cannot pull this stack out. We cannot pull out the main stack frame unless everything else is gone. So what ends up happening is that this gets put in, it stays, it runs, and then once it returns something, meaning that it's done running, this thing gets popped out. So it's the last thing that came in, and now it's going to be the first thing to go out. And then the other stack frames get removed. This one gets removed once it's done executing. And then once we're left with the main, and this returns 0, because remember, the main is just a function. It is going to return an integer, and the integer is going to be 0 once the program runs successfully. So this will get popped out, and then the stack is empty, and your computer is like, hey, your program ran successfully, good job. Now I can use this memory that you once occupied for something else. So this is something to keep in mind. Whenever we call any function, it generates these stack frames, even the main function. So recursion plays a bit differently because we have to keep in mind that recursion is a function that calls itself. So in this function called recursion, within the body of the function, which is right here, we are calling the function again. And keep in mind that we're incrementing this so we can hit towards the base case. Just like how in the loop, we have to increment towards the terminating case, which is the base case. So because this is a function that calls itself, and since in the stack, whenever we call a function, a new stack frame is generated, the thing about recursion is that recursion generates multiple stack frames. And this is one of the downsides of recursion, but it's also the upside. There's some special tricks that you can do with these stack frames that you can't do with loops. And we'll dive into that soon. So let's say we call this, so let's say we go here and we call the recursion. So what this is going to do is we have the main function running. It is now going to generate a new stack frame. And this is going to be the recursion. a stack frame, but remember that in the stack frame, our I is going to be equal to 0. So we're going to go here. This right here is going to be false because 0 is not equal to 5. It's going to go here, print out our I, and then it's going to go here, and it's going to call itself again, but increment I by 1. So now it's going to make a new stack frame. Recursion. And then here, remember that because we incremented I by 1, this is now going to be equal to 1. And it's going to do the same thing again. It's going to be like, hey, is 1 equal to 5? No, then move on. Print I. So now I is 1. Well, we print 1 to the console, and then it's going to call itself again and increment I again. So it's going to keep on doing the same thing again and again. Okay, I kind of messed that up. Gonna keep on doing the same thing, and then it's gonna call itself one more time. So this is what's happening whenever you're really doing recursion. You're basically generating all of these stack frames. And you might notice that, hey, this like jar is getting pretty full. And this is one of the problems with recursion, is that recursion uses up a lot of memory, and it can overfill the stack. And if you've ever gone to a site called Stack Overflow, it basically talks about this. Whenever we keep on calling functions into our stack, so much so that our stack runs out of runs out of space, our stack overflows. So kind of like how if you fill the jar with water, if you kept on filling it up with water, there'll be a point where the water starts to overflow. And this is bad. You don't want to leave a mess in your computer's memory. So your operating system will come in and be like, ah, this is a stack overflow. Terminate the program. Stop it. It is overflowing. And I can actually demonstrate that if I was to infinitely call recursion, but I'm not going to. Or actually, maybe I should. Yeah, how about we do that? Let's take a break and let's cause a stack overflow. So let's just do while true. So basically now what we're doing here is we're making this gone. We're giving it no base case at all. So this loop is going to go on forever. It's basically going to keep on incrementing, keep on calling recursive calls until my operating system is like, dude, you are over flooding my memory. I am going to terminate you. So let's do that. Teaching. Let's see. Oh, it didn't. While true. Oh, sorry. If false. Cool. Okay. Well, we got a segmentation fault, not really a stack overflow. I wonder if it'll stack overflow if I do segmentation fault. Okay, I guess I got a segmentation fault and not a stack overflow. Segmentation fault is basically, let's see what segmentation fault actually means. Cause a memory that does not belong to you. Yes, but yeah, that's not really stack overflow. Yeah, I wonder why it's not doing a stack overflow and why it's doing segmentation fault instead. Is it allocating memory? I+1. Okay, actually, if I was to Okay, let's see if this... No, it's still segmentation false. Okay, let me... Still segmentation fault, okay. Okay, what's this red? Recursion. Recursion. Oh, spec something. Okay, let me... Will this work? No, still segmentation fault. Okay, let's just make it really simple. It should Stack Overflow. Okay, it seems to... Actually, if I was to just call main infinitely amounts of times, this should... Oh, okay, I guess it calls it segmentation fault, even though I keep on calling main infinitely amounts of times. Okay, let's undo. Cool. So anyways, back to here. So yeah, this is a Stack Overflow, or yeah, I'm not sure why it's segmentation faulting, but yeah, it is Stack Overflowing because we're calling the function way too many times and it's filling up our stack. And I believe on Mac OS, our stack is about 1 megabyte, so which is 1 million bytes of memory. And typically these programs take very little data because it's honestly not super complicated. So we have tons of space. So the only time when you really Stack Overflow is really when something goes terribly wrong, because no normal program will ever occupy 1 million bytes in the stack. The only way that it will occupy 1 million bytes if there's a bug that causes it to infinitely recurse or infinitely call functions that just overflow. So yeah, so that's the stack. And yeah, you can really think of the stack as a cup. That's how I think of it. So let me go back to here. So as we go up, we have int I equal to 0. This is going to be false. It's going to print out, it's going to increment, and then it's going to keep on doing the same thing. So it's going to be 0, 1, 2, 3, 4. So once it gets to I is equal to 4, so it will print out 4. So remember that, like in our console, what we're doing is we're going to print out 1, 2, 3, 4. Because remember that we go from main, we print this, so it gets so the 0 gets printed, and then this one calls the 1, so the 1 gets printed to... oh shit, I forgot my 2. Can't count. Okay, 2, 3, 4. So we're going to print 1, 2, 3, 4. And then once I is equal to 4, it's going to come here, do 4 plus 1, which is 5. And then it's going to check this, like, hey, if I is equal to 5, which it is, because now I is 5, we are just going to return, meaning like we're going to tell the computer that, hey, our function is done, where we are going to return. So now, once this returns, it's going to go here. It's going to do one more recursive step. The I is going to be equal to 5. And then when I is equal to 5, we just return right away. So because it's going to return, this isn't going to get printed. if I had moved this up here, this would print, so it would show 5. But because it hits the return before it gets printed, the 5 never prints. So once it returns, it gets first out. So it will get popped off the stack. So this will be popped off. And then since here we are gonna since we are turning what recursion 5 gave us, which is a return, this will now this this will just be like, okay, you're done, I'm done too. So now that's gonna return. So this will get popped off, and then 3, and then 3 is going to return since 4 returned, and because 4 returned, we know that when I is 5 returns, and then 4 is going to return, then 3 is going to return, then 2 is going to return, and then 1's going to return. It's kind of like dominoes, um, like you know those like little games that you played where you like stack these like checkers up. And then once you knock one of them over, like, all of them get knocked over. It's kind of like that. So, this is going to return, it's going to get popped off. This is going to return, it's going to get popped off. This is going to return, it's going to get popped off. This is going to return, it's going to get popped off. So basically, we're going to empty out the stack because they're all going to return just like a series of dominoes. And then we get to the main, and then finally, the main is going to return a 0. To tell our operating system that, hey, the C++ program ran properly, we are now done, you are now free to use the stack for something else. So that's how recursion works. It's basically the same thing as a loop, but just another way of writing it, and it has some unique properties, such as the stack and how it works in the stack. So the stack can actually be used to our advantage. And I can show you guys how using a branching example. So in class we went over an example where we had a recursive program to print all of the possible binary digits that are 3 digits long. So for example, it print 000 all the way up to 111, and it prints all possible combinations, or the technically correct term is permutations. So printing out all possible permutations in a loop sounds a bit daunting, because you probably have to have, I'm guessing, some nested loops to handle to handle, like, so example, you have to handle everything that starts with 0, everything starts with 1, and then here everything that starts with 0, and also everything that starts with 1, and then everything that starts with 0, and everything that's 1, and it seems a bit daunting to write that out using a for loop. You can do it, but it'll be long. So one of the beautiful things about recursion is we can actually utilize the stack memory to our advantage and kind of let it do the work of a complicated for loop in a piece of code that's actually like relatively small. So what our professor did was he kind of introduced us to like a binary tree. Binary tree is kind of like something that starts off as a node, and then it branches out to 2. So this is where binary comes from, one or the other. And this branches off into 2, and this branches off into 2. and then this branches off into 2, into 2, into 2, and so on. So this is a binary tree, and it's called a tree because it kind of resembles a tree, kind of like how a tree has branches, and then those branches have smaller branches. Do you guys see the similarity? Kind of a tree. So, okay, I don't have brown, but yeah, hopefully you guys see the similarity. So he kind of introduced us to a binary tree, and recursion is really good for traversing these binary trees. Like recursion makes it easy for us to kind of explore all possible like all of these nodes in this binary tree using recursion. So what we're going to do is we're going to use recursion to basically start here, and then let's say that the base case is going to be one of these guys. So we're going to use recursion to navigate towards the base case. So we're going to go here, we're going to go here, and we're going to go here. And then we're going to print, we're going to go back here, we're going to go here, we're going to go print, go back here, go back here, go back there, go back there, print, go back there, here, print, go back here, go back here, go back, go here, print, go back, go here, print, go back, here, go here, go here. Okay, you guys get the point. Um, so we're going to use recursion to traverse this tree, to basically explore all possible values of this tree. And this is called branching recursion. And branching recursion takes advantage of the stack. So essentially, maybe I should show the code first, but uh, I'm gonna try to give you guys a conceptual idea. Also, these binary trees are all often like that, but just for illustration's sake, I'll do it like this. So, so we're gonna have a stack frame, and this is gonna represent this node. And this like second tier, these second tier nodes are going to be stored in this stack frame. And these third tier nodes are going to be stored in this stack frame. And these fourth tier nodes, which have our base case, are going to be stored in this stack frame. And then these are going to pop in and pop off. Okay. So yeah, and also I believe this is what our quiz is going to be on Tuesday. So let's look at binary trees. Yeah, so kind of like what I drew. I just drew the upside down version of it, so it kind of makes sense on why it's called a tree. So we have a root, then you have these child nodes, and then these child nodes get deeper and deeper, just like a tree branch. So we're going to use recursion to explore this tree branch, and what's going to happen is, because we're going to want to print all possible values of what the heck is this? Okay, anyways, because we're gonna want to print all possible values of like 3 binary numbers, and also it's called traversal. So when you're like navigating a tree, we call it binary tree traversal. Yeah. So yeah, tree traversal, exploring each node. And yeah, typically we use this in recursion. I think yeah, so here. So recursion lends itself very well into like navigating these like data structures. And also this is a data structure. So this is a way of representing structuring data in a certain way, where this data is a child of this node, and this data is a child of this. So that's a data structure. Also, you could also think of this as a family tree, whereas the top is like your grandfather, your grandparents. The second level one is your parents, and the third level is you and your siblings. Okay, so let's try to print binary. Okay, so what we're going to do is first I'm just going to write it out and kind of walk you through how I'm thinking about it. Also, this code might not work. I'm just learning just like you guys are, but I'll do my best. And you can skip ahead and see if it worked or not. Okay, so we are gonna print out all possible binary combinations. So that's our goal. So what our base case? So first you have to think of a base case. So just like how for a loop, we're gonna initialize the loop, and then we're gonna have to start think of a stopping condition. So let's just make the function header. So the function header, actually I'll just do it in VS Code. So the function header, so we don't want it to return anything because we're only going to want it to print stuff. And also the stuff I can get rid of. And this stuff too. Okay, we don't want it to print stuff. We're only going to, so we're going to, actually I should leave the loop so it's easier to understand. So we're going to, okay, so we're going to want to print out a string. So let's include a string. So std string, and let's pass it in as reference. Cool. Oh, comma? Cool. So we're going to pass in a string as reference. Okay. And the string is going to be blank. So we're going to have to initialize the string here. And we're going to pass in that string. Okay, so we're going to start the increment to here. And because we're going to want to print out 3 binary characters, what I'm going to do is I'm going to add digits to the string. And because we only want to print out 3, the base case will be when the string has 3 digits. So I'm going to do like if I, actually, yeah, it's supposed to be 3. Or actually, I can just pass in an I. So let's pass in at 3. So if I, so what we're going to do is rather than doing plus plus, we are actually going to decrement. So we're going to do I minus minus. So we're going to do if I, so here I'll just kind of do the same thing so you guys can follow along. This is really what I'm doing here. If I is less than or equal to, yeah. So this is really what I'm doing here. So I'm going to do is I is equal to 0. Let's do, let me think. Should I do the SED count? Yeah. SED count as. Okay. So we're gonna, so this is our base case. And when you hit the base case, we are gonna print the string. Okay. So we have our base case now. And our string is empty. So we need to decrement the string. I mean, decrement in the index so we can head towards the base case. So what I can do is I can do recursion. Actually, I can, oh yeah, I forgot to do return. I can do return. Actually, no, I don't want to return yet. I can do recursion I minus 1. So first I have to do string. So S, so let's add, so because we're going to navigate the leftmost side of the binary tree first, what we're going to do is we're going to add zeros. So what I mean by that is because this is how we're going to start off with, we're starting off with an empty string, right? So the way for us to go here is we're going to have to add zeros. So we're going to 0, 0, 0. And then this will also represent our I. So because I here is equal, so here I is equal to 3, we're going to add a 0, then we're going to turn I is equal to 2. Going to add a 0, then I is going to be equal to 1, and then we're going to decrement I again, and I is going to be 0, and this is when we print. So we're actually going to print this. So let's first start off by printing this. Okay, and also this may sound a bit confusing, but try to bear with me. I'll like write up first and then I'll try to explain what's happening. No, I want to, okay, I want that on. Okay, so we're going to do S plus, let's add a char 0, and then I minus 1. Okay, let's, okay, why is that red? What's a string? S plus equals? Yeah, okay. Okay, so now if we were to print this, we should get 3 zeros and then return. You can just write a return at the end. Why is that R? Okay, cool. This should work. Hopefully this doesn't segmentation fault. Cool. Okay, so now we've printed out 3 zeros. So this should be pretty self-explanatory, but I'll try to explain what we're really doing here. Okay, so this is now printing out 3 zeros. So basically what we've done so far is out of this binary tree. Well, we haven't really built up a tree, but I am going to try to explain to you what I'm trying to do. Let's make this bigger. So far we've built this. So far we built the leftmost side of the tree. So, and the rest we have to build the rest, but don't worry about the rest. Okay, so far we built up the leftmost side of the tree. Also, feel free to pause and try these experiments yourself. You learn programming by doing, not by watching. So be sure to practice. Okay, so what I'm doing here is I'm initializing an empty string, and I'm passing in this integer 3. So this integer 3 comes in here. And I'm also passing the string as a reference, so we aren't making copies of it. So here, this will fail because we know that 3 is not equal to 0. So this gets ignored. And then what happens is our string gets a 0. So now our string, so here our I is equal to 3, right? So our string is blank. So I is equal to 3, and our string is blank. So now we're going to add in a 0, and then we're going to decrement I by 1. So now we're going to make a new stack frame. So remember how so like here, rather than I being 1, 2, 3, where we are actually going backwards. So I will actually erase this, so it kind of makes more sense. So I is equal to 3. So now we're going to decrement I by 1. So now I is equal to 2. But now our string has a 0. And then we know that 1 is not equal to 0, so we're going to do the same thing again. Where we're here, now our I is going to be equal to 1, and our string is going to have 2 zeros. And then we're going to do the same thing, because we know that 1 is not equal to 0. We're just going to do this again. So I is going to be finally 0, and our string is going to be 3 zeros, just like that. And then finally, because 0 is equal to 0, this is true, we're going to print out our string, and then we're going to return. And then once this returns, so remember here, so 2, 1, 0. So this is going to return, and then this is going to get popped off. And then because this program was paused right here, remember how we decremented? It was paused right here. Once that returns, we know that this line of code has finished. So now the compiler is going to go down, and then it's going to hit this return, and it's going to be, okay, you're done too. And it is going to pop this off. So this is a very important thing to know. So remember that in each of these stack frames, the program gets paused right at the recursive call. So all of these previous versions of the function are paused right here. So remember that any code that's over here will only run once the base case hits. So something to keep in mind is that code over here runs before base case. And then code over here runs after the base case, because this is where it gets stopped, and then the function is called again. So keep that in mind. That's very important. Okay. So yeah, so here we start to print it. So remember how, so like I said, because this is going to return, what we can do is rather than, so once it's 0 and we get the return, rather than exiting the function, we can actually just call the function again. And then this time instead, add a 1 and then decrement I. So what this is going to do, and also this is a very tricky part, so pay attention. So what this is going to do is that, remember how I said that, so the 0 is going to print, okay? The 0 is what prints, and then it returns, and then it goes back here. And keep in mind that in here, the I is still 1. So when the I is still 1, we can decrement I again back to 0, but then we can actually add a 1 at the end. So what this is going to do is we're here. We print here, right? So these nodes are the printer nodes. Okay, so when these nodes hit, we print because that's the base case. So when I gets to 0, this also returns, right? Also, you can also think of return as in like go back. So now this is going to return here. But here, keep in mind that I in this node is 1, and the string is 2 zeros. So what we can do now is we can call the function again, but then add in a 1 at the end. So now we're making this. And now here, the string is going to be 0, 0. And because we're going to add in a 1, it's going to print 0, 0, 1. And then because our I is now going to be equal to 0, it will return. So we'll go here. We will print out the 0, 0, 1, and then we will return. And now guess what? Once, so this is run, and now this has run. So now we go back up the tree. So now we go back to I is equal to 2. So remember, these things are now popped off. Okay? So now we're going to go back to I is equal to 2. And guess what's going to happen at I is equal to 2? So this has so this has run. And now we are going to run this. So now when the I is equal to 2, we're going to make a new branch. And we're going to decrement I by 1 and add a 1 to the string. So now here, our I is going to be 1 again, but our string is going to be 0, because remember how at 2 our string is just 0, right? We are going to now add in the 1. So now our string is going to become 0. Okay, so if you're stuck, pause and go back, because this is the pattern that's going to print out all of the numbers for us. So make sure you understand this. Okay, so our I is now 1, and our string becomes 0, 1. Okay, so now our string becomes 0, 1, and this function calls the whole thing again, and guess what? 1 is not equal to 0, so this won't execute. And also, I should probably erase so it doesn't get messy. Oh no, I don't want to erase that. So now our I is equal to 1, so that doesn't run. And now it's going to go back to here again. So this is going to keep on running until the return statement hits. And then once the return statement hits, then this line is going to keep on running until the return statement hits. And then once these two are done, then we're going to return and we're going to make a new node again. So that's the pattern. So I'll do one more example because I don't want to build up the node by hand, but just to kind of demonstrate what's really going on. So remember how now, because these two ones ran already, our I is back at 2. So our S can be equal to 0. And So our I is 2. Yeah, so now we're on this line right here. So now we're gonna add in a 1, which we did. So it's gonna go here, it's gonna add in a 1. And then it's gonna call the function again, and here it's gonna be 1 is equal to 0, which is false. It's gonna go here, then it's gonna add in the 0 again. So it will go here, and it'll be 0, 1, 0. And it will print because now our I is at 0. And it's going to print 0, 1, 0. And then it's going to go back. So this is done. And now it's going to go here. And it's going to go add in a 1. So it's going to go back, like I said. And then it's going to add in a 1. And it's going to print 0, oops, 0, 1, 1. So now this is going to print. And now that these two are now done, they're both returning. We are just going to return and we're going to go back up the tree. So this is done, and this has hits a base case. We're going to go back here. And because when s is equal to 2, when this has fully done, because this is now fully done because we have explored all of the tree, like basically like when s is equal to, I think, 1. So when s is equal to 1, this is now finished executing. Now we're going to go here and we're going to return. And we're going to go back here. So in this stack frame, where I is equal to 3, in this stack frame, only this part of the code has been done executing. Now we have to, oops. Now it is our turn to do the whole thing again, but now we're going to execute this. So now we're going to add ones. So is it going to go here? Now it's going to do 1. And it's going to repeat the same process again. Branch of more nodes, do 1, 0. Here, it's going to do 1, 0, 0. Then it's going to go back here and do 1, 0, 1. Then once that's done, it's going to go here. Then it's going to go here and do 1, 1. Then it's going to go here and then do 1, 1, 0. And then 1, 1, 1. So that's how we're going to build up the tree, which is kind of like this. So I know that's a lot. I hope that kind of makes sense. I think after you see it kind of go through here and then go here, then go here, you do kind of start to see the pattern, and that pattern will just continue because remember, the program only executes when this last stack frame hits the return. Until the last stack frame hits the return, it is just going to go through all possible combinations. So yeah, I hope that made sense. Let's actually see if my code actually works. Oops. Okay, so like I said, going to recursion s plus 1, do I minus 1. Did I spell recursion wrong? Plus equals. Cool. So here's the moment of truth. Oh no, what's going on? Okay. Oh, this is actually adding in. Oh, I think I have to do. Hold on, let's see. 1001. Okay, let's see what happened here. Do you have to do a space? Or am I not clearing the string? I think I'm not clearing the string. Okay, if you empty out the string, will it work? Okay, 1 1 0 0 0 1. God, this is embarrassing. Okay, let's see. 0 0 1. Cool, I made a cool pattern at least. Yeah, okay, I'm printing here. Yeah, actually, no, I should need to clear the string. Okay, let's see. Oh, maybe it's because of the recurrence. Uh, no, I don't think that makes much sense. Let's just see how he did it. Where is it? What's it called? Two? No, that's sorting. Okay. Okay, so this is how professor did it. He did, so same thing here. Then you do plus s plus 1. Oh, he initializes the string. Okay. Would that work? Maybe it's because the string has memory. I wonder if I honestly wonder if I remove this, if I make copies of the string each time, so I don't keep modifying the same string. Okay, I'm printing something. Okay, let's just, okay, that's 0. Okay, it is interesting how it doesn't complain when that happens. Cool. So we really don't need, yeah, we really don't need I is equal to. Let me just hard code it. Okay, okay, now it works. So, okay, why was that an issue? Is that a plus equals? Is it? I think it's because like the number of prints is right. It's just that I think it's because I kept on modifying the string. And what I need to do is I need to give it a new string each time. Like I like making sure all the children of the node don't modify the string. Yeah, so now it has its own copy each time. Interesting. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so it says 8 children. 4, 5, 6, 7, 8. Yeah, so like it was, so it's still properly traversing it. It's just that it keeps on adding stuff to the string. Yeah, I see. Interesting. Anyways, yeah, so that's really what's happening here. So we're just traversing. So basically the bug was that like the string was being remembered. So when it was 000, it would go here and then do 0001 and then go back here and then do 000101. And just like what it would do is as it was going across, it was just like adding this to this to this to this to that to that to that because the string was being remembered. So that was the issue I was facing. Anyways, so yeah, so that's basically what we're doing. And we're doing that because remember what we're doing is we're popping in stuff. We're doing the computation, we're hitting the base case, and then we're popping off. And then this has two stages, so it pops in a new one. So there's one that adds zeros, and there's a stack that adds one. So basically, what it was doing, it was adding in the recursion that adds the zero, prints the one that has a zero, pops it off, and then, oops, and then it would go here to the thing that's doing the +1, and then it would add in the thing that has the one, add in the one, and then the thing that has the one would also have its own thing that adds in a zero and a one. So if it was to kind of like, if I was to make a jar, I think, kind of be like this. So we have the main, and then we have the recursion. So the recursion would have one that adds a one, and the function, actually I think it would go like this. So this one calls in, so this is what's happening in the stack. So it's going to call in a function that adds in a zero, then it's going to call in another function that adds in a zero, call in another function that adds in zero, and then here it's going to print. So here it's going to print 000, and then it's going to go, this is going to go back, and then this function is basically gonna call the other function that's gonna add the one. So now it's gonna print 001. And then this is gonna be done. Now it's gonna go back here, and then it's gonna call the function that adds in a one. And then this is gonna add in a function that calls a zero. So it's gonna be zero, so 0, 1, 0. And then this is gonna function that adds in a one, so 0, 1, 1. So that's really what's happening in the stack. And then this happens again. So this one would print 1, 0, 0. This would print 1, 0, 1. This one would print 1, 1, 0. This one would print 1, 1, 1. So that's kind of what's happening and within the stack. But it's really just like what it's really doing is it's just popping in and popping out, popping in and popping out, and once it's done, this one's gonna do the same thing. So this one's gonna get popped off, and then this function is then gonna pop in, pop out, pop in, pop out. So it's gonna do all of that stuff. And then if you notice that this looks like a binary tree too. Here, actually, I'll draw it in different colors so it's easier to see. Yeah, do you see how it looks like a tree? Yeah, so yeah, we're making trees using recursion. Okay, so yeah, that's branching recursion. So yeah, so that is branching recursion done.